example that we didn't quite get to in class last time, which is the two blocks attached to each other by a massless rope and then placed on either side of this frictionless asymmetric double ramp. So the rope runs over this ideal pulley, so it's a massless pulley, and that means that the tension is the same on both sides. It's at the apex of this double ramp. The first block is on the side with a incline of 45 degrees, so we'll go ahead and just write that in here, into the diagram here. 1 second. All right, so let's see if we can write this in here, 45 degrees. And it has a mass of 10 kilograms. So we'll write that down here, maybe 10 kilograms. Okay, and we want to know what the mass of the second block would have to be on this side with an incline of 30 degrees in order for the system to be in equilibrium. So let's take a step back here and think what that means. We want to know what the mass of this object is in order for the system with M1 and M2 connected with this rope across this pulley to stay stationary, basically not to move. And that means that the forces, if the system doesn't move, then of course that means that neither mass individually is moving. So that means that we can look at either one of the masses and say that the net force on this mass must equal to 0. Because if the net force is equal to 0, then by Newton's second law, we have the acceleration is 0, and so it stays stationary or in a state of constant velocity, which is the definition of equilibrium. And in this case, we're taking it in a state where it starts at 0 velocity and ends at 0 velocity, or continues on in 0 velocity. So we're trying to find a case where the net force on M1 is 0 or the net force on M2 is 0. Either condition is sufficient. All right, so let's go and see how we might tackle this. Well, the first thing we want to do is we want to realize that we need to define an axis. Now what we can do is, if we're clever and comfortable enough with it, we can just say, hey, this is a 1D problem. The only direction that matters is motion along the incline, which then changes direction, but only direction when it gets to this pulley. And so that direction is along the incline this way. But it's really kind of a 1D problem. It's going to be a bent line that goes up and then goes down at this angle. Right? But if we want to be just a little bit more formulaic, then what we can do is we can define on this side an axis like this, and call the one that goes along the incline x prime. And over on this side, let's get this over a little bit more so I have some more writing room, we can define an axis that goes like this. Excuse the axis being a little wobbly. Right? And we can call this one x double prime. So positive x prime after the pulley becomes positive x double prime. And of course there's a y prime and a y double prime here if we want to be completely explicit. This dimension would be y double prime. But if we look at just, say, the left half or maybe the right half of either one of this equation or this problem, it looks a lot like the problem we've already done in the past of just a block sliding down an incline. In other words, we previously showed that, if you go and look back at the example, that the gravity acting on mass 2 was pulling straight down. Right, so I had to restart a little bit because I completely lost my voice for a moment. So we had the force of gravity pulling down this way, right? So we can, 1 second, get back on here, move this over a little bit more here so it stays centered on here. So we have a force of gravity pointing straight down. Right? And what we could do is we said we wanted to break this up into a component along the x prime, in this case x double prime axis, and one along the, oh, that's really a bad axis there. Let me see if I can do better than that. We wanted to have a component along the x double prime axis and the y double prime axis. And when we break this up, we see there's a component that runs like this. Right? And we can call that force gx double prime. And then we have a component along here, and that would be fgy double prime. Right? Let me maybe even zoom in a little bit so we can get a easier writing here. Okay, so we have this component of this, the force itself pulls straight down because that's what gravity does, but it had a component that was along here and a component that was along here. And we recognize that this component was perfectly counteracted by a just enough force, a normal force, perpendicular to this inclined surface that pointed upwards. Right, so we have a block like that. So upward on a block like this, and this perfectly cancels that, so that by definition of what the just enough normal force does, so all that's left is a force, a net force along the direction of the travel, which is along the incline. Now, what we then did was we said, by a little bit of trigonometry or geometry, we said that angle is the same as that angle. right? And we saw the logic of this as if this tilt starts to go to a smaller and smaller angle, then this thing becomes this line, which is perpendicular, starts to go more and more vertical. And as that becomes more and more vertical, the difference between these two lines will get smaller. So as this gets smaller, that gets smaller. So you know that we're at least moving in the right direction. With a little bit of trigonometry, you can show for a fact that angle theta 2 is also equal to this angle, which conveniently I put the label just in the right place, theta 2. So then, if this is the angle theta 2, sine of theta 2 is equal to the opposite. I'm out of space here. Let me slide over. Is equal to the opposite over the hypotenuse, which is equal to f g x double prime over f g, right? The opposite over the hypotenuse. So that tells us that the net force acting on, I'm sorry for this, the net force acting on this block, if it were just gravity and weren't attached to anything, would be f g x double prime is equal to, bring this one over to this side, f g sine of theta 2, right? So that's really just almost a repeat of what we did last time. But we can do the same thing over on this side with the x prime axis. Right? In this case, we'll do this again. We'll draw gravity pointing down. We will go set of axes like that, x prime and y prime. Again, this angle is equal to that angle. This is the only component that survives because the normal force will cancel out this component. The y prime component gets canceled out by a normal force. And I should label this over here as a normal force as well. Normal force. All right. So that's all that's left is, again, on this block, there's a force in this direction, and that's going to be fg prime, fgx prime, where this vector right here, is fg. Right. So let me see if I can maybe just clean that up a little bit. All right. Call this fg, and we'll call this fgx prime. Okay. So by that, we can again write that fgx prime is equal to fg sine of theta 1. And now, to distinguish the two fg's, I'll put a 1 kind of in a subscript up top with parentheses for the mass 1 over here. And then over on this side, over on this side, I'll put a fg2 for mass 2. All right? Okay. And maybe to be extremely clear, we'll put a 2 up here on this. And over here, we'll put a 1 in parentheses on this guy too. Okay, so we figured out the component of the force due to this mass alone wanting to be pulled this way. And then we worked over on this side and we saw the force due to this guy alone wanting to be pulled that way. Now we have to deal with the fact that they are in fact connected. So because they're connected, this guy doesn't just slide down the block. This guy trying to go this way and this guy trying to go this way apply attention to this string, right? And what we really want is we're basically asking for a situation where if the force, well, let's look at it this way. If we look at either individual block, we can ask to enforce the fact that this block in equilibrium has to be staying still, right? We want it to be stationary, and for that to be the case, the sum of the forces on F1, sum of all the forces on 1 has to equal to 0, right? Which is equal to F net by definition on 1. Okay, so let's look to see what forces there would be. Right. We already said that, yes, there's a force of gravity, but we actually broke that down into a force in the x prime direction and a force in the y prime direction. And we said that the force in the y prime direction gets canceled out by the normal force of the incline on the block. So we could write that it is that this is equal to the force of G along x prime plus the force of G along y prime plus the normal force plus one other thing, because now, because it's not attached by the string to the other block and the other block's trying to go the other way, there's a tension in the string. And I'm going to give that a symbol 1 as well, and we should carry along these 1s here. Sorry for the sloppiness there. Still getting used to this pen. Okay. And this should have a 1 as well, but that's okay. But we already decided that this normal force exactly cancels out that y component. So that really leaves us with the statement that Fg x prime on 1 is plus tension 1, which I'm just going to write now as tension 1, so I don't have to do a lot of the parentheses, is equal to 0. Okay? And that's saying basically that Fg x1 prime vector, we should put vectors on top of all this guy, right? Because it's vector addition. I'm going to bring this to the other side, so that's equal to minus tension 1. The tension obviously points along the x prime direction. Okay? We can do the same thing for the second block, and without belaboring the point, we would just get, if we could do all this sum F2 and all that stuff, but we'll save ourselves a little bit of writing, and we'll just simply write out the results, say similarly. Fg x double prime on number 2 is equal to minus the tension on number 2 vector. Okay? All right. Sorry, I had to take give my voice another break. It's really giving out. All right. So we had Fg x double prime 2 is equal to minus T2 using the same logic here. And we have vector signs over all these because we're doing vector addition. And now we're at the point where we can say, look, because this is a frictionless pulley, this system over here is a frictionless pulley, we know that all of the direction of the tension changes. The magnitude of the tensions do not change. That was by definition of a massless frictionless pulley, an ideal pulley. So if we take we can then say, if that's true, then the tension, let's look at what this is doing. Over here, if we go back to this diagram, we have gravity pulling straight down on this one, but because of the normal force, the only thing left is effectively a force pulling this way on this block. But there's also a tension in this wire, in this cable. So we can draw, there's a force of tension 1, pointing that way. Over here, the tension points along the rope, and so it points this way. And you notice that they point in opposite directions. So tension 1 vector is oriented opposite tension 2 vector, but they're equal in magnitude, right? Because the tension is the same in the entire rope. So we can now make the claim that the tensions must be equal and opposite. So we can come in here and write, close this down a little bit more, get the picture in view a little bit if we can. And we say, so tension 1 vector is equal to the opposite, but equal of tension 2 vector. But minus tension 2 is exactly Fgx double prime, right? So I can replace this down here with Fgx double prime 2. And come over here, look at T1. T1 is minus Fgx prime, right? I have it here with minus sign on the other side. We can easily move the minus sign to this side, so I can take T1 and say that is equal to minus Fgx prime 1. All right? And now we've done a lot of work and explicit detail just to show something that many of you could have jumped to in the very beginning, which is to state that that because the normal force cancels at the vertical component, all that's left is that that the force pulling this way on this block has to equal the force pulling this way on this block for this thing to be in equilibrium. And so that was a lot of work just to show that the x prime component of the force has to be equal but pointed in the opposite direction. Here it's pointing in the minus x prime direction, and here it's pointed in the positive x double prime direction. And because of the pulley being the ideal, the x prime direction and the x double prime direction are effectively equivalent. It's just a bend. Okay, so now that we've gotten that far, we can easily substitute in what we'd found from the previous problems and just earlier today. All right, I took another break from my voice, so we'll come back here now. I think we can finish up in one last round. We're getting close. So we have that the forces along the directions of the inclines have to be equal and opposite for this thing to be in equilibrium, which is maybe something that you could, if you have a good sense, maybe you've taken some physics before, you could just write this out without having to have gone through all the explicit math. I know some of you like to see the explicit math. So we have, let's verify, we have FGX prime pointed in the opposite direction, going kind of down to the left, which is the minus x prime direction, compared to the residual force here, FGX double prime, which is pointed in the positive x double prime direction. So they are indeed pointing in opposite directions when you consider the bent line of travel is like this. If that's positive, then this is along that positive direction. This is in the opposite, which is negative direction. So now that we verified that we have the directions correct, we can simplify our lives a little bit by simply saying, let's figure out the magnitude of these guys and just write and get rid of the minus sign and simply say we're going to try and solve for the magnitude of FGX prime 1 has to equal to the magnitude of FGX double prime. Right? So this is the magnitude of each of these. All right, so the magnitudes were given up here, so let's take this up here. We worked it out at the beginning, and we found that FGX was just FG1 sine theta 1, and that has to equal to, so this comes from here. If we look over a little bit more, we had found that FGX double prime was, from that geometry, FG2 times the sine of theta 2, right? So, but we know what the force of gravity is. It's just mass times gravity, so this would be mass 1 times gravity, sine of theta 1 must be equal to m2 little g sine of theta 2. The g's cancel. Cross those out. And so now we're going to solve for m2. Right, so we're going to go up here and remember that what we were looking for and what we should have written out right from the very beginning is that we always want to know what our goal is. We always want to keep that in mind. So here we were looking for the mass that the second block had to have. What must the mass of the M2 block of the second block on the incline have to be? Okay, so let's solve this equation for M2. M2 is equal to M1 sine of theta 1 over sine sine of theta 2. Okay, and that is our solution. I'll let you save my voice. I'll let you guys plug in the numbers, but that is the entire solution. All right.